Assalamualaikum and good day everyone. In this video, we are going to continue discussion based on the charges due to polarization. Previously, when we discussed the macroscopic view, we know that the polarization vector introduced new charges, okay, where the new charges is the surface charge, okay, rho S, and the second one is the rho V, the volume charge. So in this video, we are going to analyze these two new charges. Okay, to do that, we consider this kind of structure, and this structure is applied with the electric field. Okay, I'm going to write this is our E applied to this dielectric. And as we know that when we apply an electric field to the dielectric, it will introduce electric dipole moment. So just imagine that this material is full with this electric dipole moment. So from here, we can see that it introduced the surface charge. So let's consider, or let's focus on the top one here. Okay. This will be our rho SB, our positive rho SB. Why we have B here? Because this one is the bounded surface charge density. Okay, this positive is bound to the atom. That's why we give the B here. And the second one, let's take a look at the bottom part. Okay, where here we can see that the negative charge is at the surface. So here we are going to write as negative rho SB. Okay, so now we can see that we have the positive rho SB at the top one and the negative rho SB at the bottom part. And now we can see that this rho SB will depend or will affect by the polarization vector. Okay, so from that we can write a new equation where rho SB is equal to the polarization vector dot a unit vector. Okay, where we know that this unit vector must be away from the dielectric, and due to that, I will give axis to our structure. Okay, let's say this is our x-axis, okay, away from the dielectric, and this one is our y-axis, and this will be our z-axis. Okay, so now we are going to make an analysis based on this equation. Okay, now we know that we have the E. And based on this, we can write E is equal to EZ, okay, in the direction of Z. Okay, so this is our E. And from here, we can write the P equal to PZ in the Z direction. So we get this equation based on the behavior that we observe in the equation of this one. I give the equation here based on the behavior of this equation, where P is equal to so we observe from this equation, then we come out with this equation. So when we get this one, we can analyze our surface charge. So now I'm going to label my surface charge that I'm going to analyze. I consider this one is my first surface charge. Okay, this will be my second surface charge, and this will be my third surface. Okay. At the surface number 1, I can write here at the surface number 1 when the rho SB1 is equal to P Z in the Z direction, and the unit vector of this is in this direction. Okay, so it will multiply with this, or with the dot product with the Z. Okay, while for my second surface, surface number 2, the rho SB2, the PZ is in the Z direction. However, the unit vector is in the negative direction. Okay, you can see here that the unit vector will be in this direction, okay, towards outwards of this dielectric. Okay, now we continue with the third surface. Our third surface, I will name it as rho SB3. This one will be equal to PZ in the Z direction dot Y unit vector. Why? Because this is our surface number 3, and the unit vector will be in this direction, so in the Y direction. Okay, when we have Z dot Y, this will cause 0. So this one will equal to 0. In other words, the surface charge that exists here is only surface charge number 1 and number 2. So now we already get the surface charge. Then let's take a look at the rho V. Okay, rho V will be inside this material. So this one is our rho V. Okay. And we are going to name it is a bounded volume charge. And to analyze this, we will use the divergence theorem, okay, with the negative in front. So this will be the equation to analyze rho VB. So now we already discussed the surface charge and the volume charge when we apply an electric field to this dielectric. But next we are going to discuss how these new charges affect this E applied. Okay, now we are going to look how the charges affect the E applied. So recall the Maxwell equation number 1. Okay, if you still remember, this is the Maxwell equation number 1. Okay, however, this one is in free space. Now we are in the dielectric world. Okay, so let's take a look what will happen. Okay, we are going to assume that our electric or our dielectric consists of rho V. Thus, our total rho or charge is equal to rho V plus rho VB. Okay, so this will be our total charge. And now replace this into this. Okay, what will happen? Then let's write it. Okay, we have this one. Equal to rho V plus rho VB. And this rho VB, okay, we know that this one is equal to negative divergence of P. Okay, thus, we can rewrite our equation to become okay. So we get this as our new equation here. So from here, we can write it in D term. Okay, so let's write it here. And we know that this one relate to the E using this equation. So we can write it like this. Okay, so now we know that this D and E can be found using Coulomb's law or Gauss' law. Okay, now I want to give you like a final equation where this D can be write as okay, we are introduce a new constant here, the epsilon naught R. Okay, this one is known as a dielectric constant or relative permittivity. So I'm going to write here, this one is a dielectric constant or relative permittivity. Okay, so this is the conclusion that can we see here, where this ER will show how easy the dielectric is respond to the E applied. So again, I conclude for the dielectric material, when we apply the electric field to the dielectric material, it will create a new vector named as the polarization vector. And this polarization vector create another two new charges, which are the surface charge and the volume charge. So that's all for this video. Thank you.